Okay, hopefully now.
Hello. No.
Ah. Here, I can even resume recording. Okay. So should we review a little bit first? Is that all right? Or do you guys want to get into the problems?
We normally last semester would review first, then we'd break into rooms, then we'd come back again and discuss them. Yeah.
Okay, awesome. Okay, perfect. Yeah, so why don't we do that? Cool. Okay, and then let me share my screen so you can see what I'm working with. There we go. Okay. So, like I mentioned earlier, let me get my pen. Here we go. So, well, you're in the second semester, so you're kind of already pros at this. So, you know, you've spent a lot of time working with this stuff from last semester, and you're pretty used to it. Okay. This week in lecture, you talked about ethers. Okay. My handwriting is ever bad. Please tell me. This week you talked about ethers, which, well, there's not that much new to say about them, right? Well, first, for one thing, they're not very reactive, and then there aren't too many fancy ways to actually make ethers. Okay, like it's kind of just SN1 or SN2, something like that. Okay, so when it comes to actual synthesis, let's figure that out first, right? Because we want to be able to make these somehow. Okay, so right at this point, you know the names of functional groups, you know a lot of reactions, right? So whenever we're going to start talking about functional groups, which is the way that most of the second semester of the course is structured, we usually start off by talking about how you actually make them, because then you can do stuff with them. Okay, so cool. How do you actually synthesize them? Well, why doesn't somebody tell me? What's one way to synthesize ethers?
The Williamson ether synthesis?
Yeah, there we go. Williamson ether synthesis, which is one of the few named reactions that you actually get. Okay. And it's a fancy name, but it doesn't really mean a whole lot, right? If you have something that has like a good leaving group, okay, give it something that's an alkoxide, right? So I don't know, give it O-tert butyl, right? Okay, there we go. It's just going to substitute. Right? It's not complicated. It's something that you've seen before. This is a question that you could have been asked a month into last semester and you could have gotten it, because it's just SN2. Right? Yeah, there's some iffiness about like, oh, if this is a secondary bromine, you'll get like E2 probably instead. But okay, you know, you got to be a little bit careful about that, but that's the extent of it. Okay, what else?
Oxymercuration, demercuration.
Yeah, exactly. So I'll add that alk in front of what you said, but otherwise, I mean, yes. Alkoxymercuration and then demercuration, right? And well, again, you've seen it, right? If you have something with a double bond, well, you give it something with an alcohol, right? And then some reagent. What's the reagent?
NaBH4.
Not yet.
HGOAC.
Yes. Yeah. So yeah, this guy and then NaBH4, right? because here you get this hanging HgOAc. So then you use sodium borohydride, right? And okay, you get an ether. Let me make this pen a bit smaller so it's not as bubbly. Okay. Yeah, and then you get your ether. Okay. You know that Dr. Tong mentioned at least one other.
Condensation. I forget if it's 2 words, but it's basically condensation reaction.
Yeah, I think it's usually called bimolecular condensation, or acid catalyzed condensation or something like that. Yeah, you have, you know, two alcohols, and I don't know, let's pick these two guys, right? And then okay, you put them in some kind of acid. You're probably going to have to heat the hell out of them, and you can get an ether out at the end. Yeah. So I'm not sure if Dr. Tong would test on this question. Like usually this is like not a common reaction that Orgo 2 courses test about. It's a kind of industrial synthesis. It's not like one that you can really do at normal scales very well. That being said, you see it again way later at in this course, like almost at the end when you talk about sugars. But for now, I don't know. I'm not sure what like Dr. Tong's question style is exactly like. So he might ask about it. But you know.
I think for condensation, Dr. Tong only mentioned it in the context of making symmetrical ethers. I think he said asymmetric is not very practical.
That might be it. Yeah. Yeah, that might be the case. I was thinking that as I wrote it, and then I was like, maybe you could do it. Yeah, that's probably the case. And well, as always, what Dr. Tong says goes, especially since he's the one who determines your grades. So, of course, yeah. Okay, well, can you guys think of any others? No? Yeah, I can't either. I think that's it. Right? There's 3 different ways of doing it. So you could do Williamson ether synthesis, you could do alkoxymercuration demercuration, and you could do a condensation reaction. And I think that's pretty much it. Okay. Oh, well, there's kind of another, but it's one that's like kind of special, and we talk about it on its own. Okay, so there's another one, which is, let's say we have a double bond and we want to make an ether with it. What do we do? Maybe this isn't one that comes to mind right away, and I'm sure that you're all very familiar with this anyway, but we can add MCPBA and make an epoxide, which technically counts as an ether. So this technically it counts, in practice, not really. This is like a whole separate, epoxides are like in a league of their own, right? So, yeah. Well, okay. From there, you learned like a couple of reactions. Okay, so what reactions did we learn? Okay, well, let's say you have an ether and you don't like it anymore. What are you going to do? You want to get rid of it.
Leave it with an HBr or HI.
Yeah. Yeah, I think you can only really use one of these two. I haven't seen any situations where someone uses, for example, hydrochloric acid. So stick with probably these two. Yeah, it cleaves it. So, well, I drew a symmetric molecule, but why don't I make it more interesting and make it asymmetric, right? So which side is the alcohol going to end up on?
On the secondary side,
What makes you pick that one?
because the first reaction that occurs is an SN2 reaction, and that will occur on the primary side. And then when it wants to go on this, oh wait, sorry. Actually, the
Okay.
alcohol won't end up anywhere.
Yeah, okay. Nice. That's really good because you were taking a whole like a kind of mechanism approach to this, which is great. So exactly like you said, right? We can protonate. Okay, and then we take our bromine and kind of throw it in there, right? This place. So what do we get out at the end? Well, let me draw. So we get a bromine here. Okay. Well, that's good. That's a final product. That one's not going to change. But then we do get an alcohol over here, right? But there's nothing stopping the same exact thing from happening a second time. So we protonate that again. Okay. And give it a bromine. You know the rest.
Adam, could we go over this reaction with phenols? I feel like he was talking about something in lecture with an sp2 hybridized atom and how it can't then have that second cleave. Could we talk about like why that is?
Yeah. Yeah, so that's like really the thing to well, let me write here. These are cleavage reactions. Okay, cool. That's kind of the whole like gimmick that there is with these reactions. That's like the sort of thing that like he might ask about maybe, is just what sides you can do the cleavage on. So let's say that we had a different molecule and we tried doing the same thing. And let's just pick just about the same thing. Okay, I draw these circles for aromatic rings, right? This is, you might have seen, I don't know how Dr. Tong normally writes them, but I'm lazy, so I just write a circle, right? So I just do this. You'll see plenty of aromatic rings this semester, so don't worry. Yeah, so okay, why don't we just try doing the same thing, right? First step, this should technically be an equilibrium arrow because this is a reversible process, right? Protonation is, we can go backwards. Likewise here. Okay. So the reversible process where we protonate. So OH, and there's a plus over here. Cool. Well, where can bromine attack? Let me use a different color for this. Well, let's say it attacks on the phenyl side. We've already got an issue, right? Because this mechanism just pretty much is SN2. In fact, it exactly is SN2. But you can't do an SN2 on something that is sp2 hybridized. Like this one won't work. In part, well, here I picked this like aromatic ring, which makes it like extra not likely to do SN2. But even if this was just like a regular double bond, even if we just had something that looked like this, okay, we'd protonate. Oops, that's not the structure. There we go. Okay, we could protonate, right? And, well, same thing. If we wanted to take our bromine, we can't attack here because you can't do a backside attack on an sp2 hybridized carbon. Yeah, it won't work. Well, if that's the case, then we're kind of, well, we have another option, so we might as well take advantage of that one. Okay, here we go. All right, so the bromines are going to come and attack that carbon instead, right? And then we kick this bond over, right? Use this black arrow here. Okay, and so we end up in this case with a bromine over here and this OH over here, all right? And up in this top case, we have phenol and this guy. Okay. Quick question, what happens to this? Anybody remember from Orgo 1?
Does it tautomerize?
Exactly. Is it acid or base catalyzed?
It would be acid catalyzed.
Yep. So, well, yeah, we get an acid catalyzed tautomerization. And we would wind up with this. Okay. You will see a lot of keto enol tautomerization this semester, like a lot of it. So I'll spare you the mechanism now. And I don't think you're going to be expected to know it for now. It's the, you will see plenty of it like in April. So, yeah. Okay.
But just to make sure that tautomerization, it would only happen with sort of the, I think aryl functional group. No, it couldn't happen on the phenol, right?
Yeah. Yeah, you're right. I think aryl does refer to aromatic.
I must have mixed up the words, but I meant
Yeah,
just
I know.
the
Yeah, I know what you mean. I just yeah, I want to point that out. Yeah, okay. But you are right. This is just phenol. This is gonna stay. It's done. Yeah. And then remember, this is acid catalyzed because we're doing the whole thing in a bunch of HBr, so lots of acid around. Okay, and well, every once in a while, somebody's going to try to slip a no reaction in on you, and if you have something like this and you try to give it HBr, well, what might happen? Well, I just told you there would be no reaction. Is there no reaction? Maybe I gave you a bad example.
Maybe the HBr can bond to the carbon to the right in the like the second carbon from the right.
Yeah. Yeah, so you might actually be able to do a substitution, in the, like an addition onto the alkene. Yeah. This gets a bit complicated because there's this oxygen here, which can really make things complicated with resonance structures. And remember that this adding HBr is normally Markovnikov, right? So yeah, maybe you could try writing out the mechanism. Okay, I'll pick I'll pick a simpler example because this one's really involved. So, well, if you have something that looks like this, then there's no question, right? Nothing, no reaction. Yeah. Whoops. Cool. Let's see. So what else? Yeah, there are some other reactions that were in there, right? Let me zoom out to a reasonable level. Okay. So there was some other stuff. There was like the auto oxidation, or it might just be called auto-oxidation or something along those lines. This is like where you wind up getting these weird peroxides from ethers. It's like a weird thing that you might get asked about. I don't know if you would be asked like the mechanism or what the products look like. It's kind of a like specific reaction that doesn't really show up anywhere else. But it's good to know about. And it's like always a cool story. Like every organic chemist has some story where somebody had ether peroxides stored in a shelf and they had to call in like a bomb squad or something. Yeah, you learned a bit about thioethers, which you can synthesize in the same way as the Williamson ether synthesis, just with thiols, right? What else did you learn? TIPS-Cl, TIPS chloride. This is kind of a theme in this course. You'll see a lot of protecting groups. This is the first of them, and it's the sort of thing you don't see in organic chemistry 1 very much, but now as you start to get more involved reactions, you need to be able to protect things, right? So remember that like if you have some alcohol, and I'm just gonna pick ethanol, which is, well, the easiest one to work with, right? So you could just add TIPS-Cl, which is like triisopropylsilane or something, or tetra or something like that, right? And chloride, and then, well, you just get an O-TIPS group. It's pretty easy. Okay, and then you could do whatever other reactions you want over here, especially using Grignards and really strong acids and stuff like that, because it's not going to affect what you've got going on here, right? And then how do you get rid of it?
Is it the tea bath?
Yeah. Yeah, I actually hadn't heard about this before until listening to his lecture. I hadn't ever heard the name tea bath used before. I had always just seen the reagent itself. So it's tetrabutyl ammonium fluoride, I think, or amine fluoride, right? So it's one of these. You could certainly write TBAS and be completely okay. But the thing is that fluorine really loves silicon, like a lot, like really a lot. So it's just gonna get in here and remove this whole bond. And I think afterwards you have to do an acid workup, but there you go. You just remove it. It's really easy. You'll see this whole fluorine removing protecting groups again, like at the end of the course. But this is just a useful thing to have in mind. It's a really useful tool when you want to do some complicated stuff, but you have alcohols that you need to protect, right? And well, like I mentioned earlier, perhaps the most important thing you talked about was epoxides. but well, you guys have seen a lot about epoxides, so I think you'll probably be okay with those. Okay. That was a bunch of review. That was plenty of it. Why don't we work on some problems then? Yeah. Okay. So here we go. Why don't I even stop sharing, because you guys suggested that we do breakout rooms. I haven't worked with them so much, so this might be a little bit experimental. Okay, the worksheet is on the canvas. Do you guys have like, so in like last semester, since most of you were here last semester too, did you usually just go to the canvas page and pull from there? Do you want me to send the worksheet in the like Zoom chat? Should I do that? That might be easier.
I'm not in the canvas right now, so that'd be good for me.
Oh yeah, that's a good point. Why don't I try sending the file? Here we go. Oh, it's sent. Did you get it? I hope so. Yeah, okay. There's some thumbs up. Yeah, so okay, you guys got it. Let's see, there are 10 total people. The best way I see to factorize that is into 2 groups of 5. Does that sound reasonable, or would like should do 5 groups of 2 or 2 groups of 3 and 1 group of 4? I don't know. It's up to you guys.
Groups of 3 and 4 sound all right.
Okay.